That underground space where the water flows, the groundwater exists, is called an aquifer. So it transmits water easily. The opposite of that is an aquitard, and it would be something like I was describing with a shale, where you have platy clasts that are kind of stacked up. And so the water doesn't flow through them very well. So an aquifer transmits water, the aquiclude does not. The aquifer would have a higher porosity and permeability, where an aquitard would have neither. It would have a low permeability and a low porosity. The water table is the top of the groundwater, and it separates the saturated zone from the unsaturated zone. So the unsaturated zone is near the Earth's surface, and all of the pore spaces are not full of water. They can fill up with water when it rains, but for the most part, the unsaturated zone, it's also called the vadose zone, but we'll call it the unsaturated zone. It's not full of water. Then there's the water table. You have to think of the water table as a surface. So underneath that surface, then all of the pore space would have water in it, whatever it is, bedrock or sediment. The term for that is also phreatic zone, but we'll just call it the saturated zone. Between the two, there's this thin layer that we call the capillary fringe, where through capillary action, water can kind of wick up into the unsaturated zone, but it still doesn't fill all the pore space. The depth of the water table varies. It kind of mimics topography in a way. We'll see that in another slide. In a humid setting, so let's just say east of the Mississippi, the water table is pretty close to the Earth's surface. In arid settings, so we'll say west of the Mississippi, the water table can be tens to hundreds of meters down. Perennial means that the surface water is there all the time. So surface water that is there all the time would mark where the water table is. So in this image, here's a pond. The water table intersects the Earth's surface at the edge of that pond. The same is true for wetlands or for streams. The water table intersects the surface of the Earth where you find a wetland or a stream or a lake or a pond. The water table then is going to move when it rains, and during drought it can also drop. So here in this table, this graph, in the top part of the graph is the rain. So it's raining, and every time it rains, whoop, 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 the water table responds. So water table goes up and down as the rain goes up and down, and we can measure that in a monitoring well. So let's see, water table position changes with rainfall. During seasonally rainy periods, the water table rises. It's closer to the Earth's surface. And then when we have drought, the water table is going to drop. So this image here shows what it would look like if this was a pond or a river, and then we had a drought, the water table drops, and then the pond or river there dries up. Okay, so here is the water table and showing the topography of it as the topography of the Earth changes. So we have a mountain, a valley, a mountain, a valley, and the water table has that same shape. It's going to rise and lower and then rise and lower. The water table, yeah, there it is. So, when it intersects the surface is where we have this river and also where we have the pond. There are special kinds of water tables. Get me out of my way. This is a perch water table. So here is an impermeable layer or an aquitard. Here's an aquifer, and up here above the regional water table, so a region has a water table, above that there may be a little lens of an aquitard, some kind of impermeable layer, usually like a clay, and above that clay there can be a little perched water table. These perched water tables can trick you. It can be like a false water table. So if you tap into that aquifer to uses your drinking water, it may run out. You're like, what happened? Why did the water run out? And it could be that you just have a tiny little aquifer there above some impermeable layer. All right, groundwater flows. It's not just staying in one place. It flows because of gravity. It infiltrates down, so that's a flow, right? From the surface, precipitation, usually it's going to flow down and hit the water table, and then that groundwater is going to flow. So it goes downhill, so it has some topography to it here, and the water hits the water table and now it's going to flow down to the lowest point, which is the stream here. Water table, or excuse me, groundwater flow can happen at different rates. And usually near the surface, the groundwater flow is going to be faster. So in this image, like we can measure the flow in years. Below that, a little deeper, we would measure it in centuries, and then millennia, maybe thousands of years. So groundwater flows at different rates depending on the depth of the depth you find that water in the aquifer. Okay, recharge and discharge. There's a recharge area for an aquifer, that is the surface above where it rains and that water all flows into that aquifer. There's also discharge. So discharge would be water leaving the aquifer. It's discharged when streams take some of that groundwater. That would be a stream that is a gaining stream. It's gaining water from the groundwater. Sometimes streams lose water to the groundwater, but gaining ones will take groundwater to keep up their flow. All right, flow rates. We can measure the flow rates. There's a law we're not going to talk about called Darcy's Law, and it takes into account the porosity of the material and the gradient of the gradient or the slope of the water table. So if there's a high slope, then the groundwater will flow faster. I'm gonna let my dog out before she cries or breathes out. Back. Where were we? Darcy's Law. The gradient or the slope of the water table matters, as does the porosity of the material. So those taken into account, don't worry about the equation, will give us a high or a low velocity of the movement of groundwater in the subsurface.